So here we're looking at 4 different velocity profiles, and in all 4 cases, u infinity, the free stream velocity, is equal to 0.05 meters per second. The question is, why do the velocity profiles look so different? For example, the velocity profile on the top has a much thinner boundary layer than the velocity profile on the bottom. The thickness of the boundary layer in the case on the bottom is very, very thick compared to the thickness of the boundary layer in the first case. The reason they're different is because the properties of the fluids are different in each of the 4 cases. So as I've shown here, the surfaces tend to have a smaller effect on fluids that have a small kinematic viscosity. It tends to have a smaller effect on fluids that have large densities and small dynamic viscosities. Loosely speaking, this is a little bit like saying the sum of forces is equal to the mass times the acceleration of the fluid. By analogy, the density of a fluid is sort of like is its mass. The forces acting on the fluid are associated with viscosity or associated with mu. And the acceleration, therefore, is related by analogy to the sum of forces divided by the mass of the fluid. The acceleration of the fluid, therefore, would be small if the fluid density is high, if the mass of the fluid is high, and the forces acting on the fluid are relatively small. With those ideas in mind, we can examine the thickness of the boundary layer. This very thin boundary layer in the first case might be indicative of a fluid that has a very large density, for example, or perhaps a fluid that has a very small dynamic viscosity. It has a very small kinematic viscosity. And the other extreme, velocity profile that looks like the one on the bottom, would be indicative of a fluid that has a very small density and a very high dynamic viscosity, or a very high kinematic viscosity. Because the Reynolds number is defined as the density of the fluid times its free stream velocity multiplied by the coordinate position x divided by the dynamic viscosity, we find that fluids or conditions in which the Reynolds number is large, it results in a smaller effect on the fluid. Let's look at a case in which we've got a really large Reynolds number. So in this fluid, it turns out I used properties for liquid mercury. This fluid's got a really large density and a really small dynamic viscosity. If we look at it, we could examine a location within our velocity profile. And when we look at the movement of that fluid, it just translates, and there's no deformation of the fluid itself. So no matter where we pick, we find that the original shape, it doesn't deform at all. The only place in which it deforms is near the surface, or kind of within the boundary layer there. And we see that the original square shape deforms into a trapezoidal shape. Even closer to the surface of the plate, we see a large deformation of the material, but only in regions that are relatively close to the plate. Again, far away from it, we don't see much deformation at all, just purely translation of the fluid. Let's contrast that with this velocity profile, and I use parameters for air for this velocity profile. If we examine this, again, outside of the boundary layer, we see translation of the fluid with very little deformation whatsoever. However, when we approach the boundary layer, get somewhere in it, we do see a deformation of the fluid into a trapezoidal shape at regions within the boundary layer itself. And this deformation becomes more and more significant the closer we are to the bottom of the plate. In fact, at the very bottom, the shear rate on the fluid is the highest. So towards the leading of the edge of the plate, again, we see a very large shear stress at the leading edge of the plate. Finally, this bottom case is a situation in which the fluid has a very large dynamic viscosity and a relatively small density. And the fluid I've chosen here is akin to cooking oil or motor oil, for example. And when we examine this scenario, we'll see a very large shear stress acting on the oil itself, no matter where we are in the velocity profile. The velocity of the oil tends to be smaller closer to the plate than further away. And when I label these 4 velocity profiles, I've got mercury on the top, followed by water, air, and oil on the bottom. So despite the fact that their free stream velocities are all the same in the 4 cases, we see very different velocity profiles. Fluids like mercury with a large density and a small dynamic viscosity tend to be impacted less by the surface than do fluids like oil, which have a very large dynamic viscosity and a small density.